Hello everybody. Today we'll talk about speed of sound underwater. So sound is a vibration that propagates as an acoustic wave through a medium. They need a medium to propagate, for example, air, water, steel. They cannot propagate through a vacuum, which is a lack of medium. And speed of sound is a distance traveled by sound in unit time. The speed of sound depends on various factors such as temperature, pressure, density. So let's investigate how it changes underwater in the ocean. If you want to learn more about speed of sound in general, check the link in the description below. So let's calculate the speed of sound in water. Consider a sound wave propagating through a surface of water at atmospheric pressure and at a temperature of 20 degrees C. Now we're going to assume certain properties of water, such as density, which is 1000 kilogram per meter cube, and bulk modulus at this particular temperature. Now if you plug in the equation, we can calculate the speed of sound to be around 1476 meter per second. It's going to hover around based on the density and bulk modulus, but it's around this range. So let's perform an experiment to determine how the speed of sound may change underwater. Let's consider a person inside a submarine located at ocean floor and another person inside a boat who's located at ocean surface, so just above the person on the submarine, and both have a task. That is, they have to measure the speed of sound in a beaker filled with water. So they're going to have a beaker filled with the exact same water, and they have to measure the speed of sound in the water. So, given that the submarine maintains the exact same conditions as the boat, what will be the speed of sound? Will it be different or will it be the same? So, here's a schematic. So, the submarine is on the ocean floor and we're assuming a depth of, let's say, 3,000 or 4,000 meters. It doesn't matter. And both have the task to measure the speed of sound. Now, the speed of sound is going to be the same in both cases because the conditions are maintained the same. Both are measuring the same water, which is at the same temperature, same density, same pressure, so it's not going to change. So the takeaway here is that the speed of sound doesn't change with depth, rather the conditions at the depth. So for example, if the person were to get out of the submarine and measure the speed of sound in the water at this great depth, then the values will no longer be the same because certain conditions change with depth. So there are two things that change at the ocean depth which are of great importance. Those are temperature and pressure. So ocean, what is an ocean? It's a body of salt water. It covers 70% of the Earth's surface. The ocean's temperature and pressure vary as the depth increases. The ocean surface is heated by the sun during the day and it cools at night. So here are some three pictures depicting different regions of the ocean. So on the left, you see the surface of the ocean, and closer to the surface, the sunlight reaches. But then as you go deeper, there's this twilight zone where there is very little sunlight. And if you go at great depths, there is just nothing. It just looks black because there is no light penetrating at that great depth. So as the ocean depth increases, the water temperature decreases, reaching very close to 0 degrees at the ocean floor. However, the water doesn't freeze. Additionally, with the increase in the ocean depth, the pressure also increases. You can think of it this way: as you're going deeper and deeper, the entire water column above your head is exerting pressure on you. So if you're going like 3 or 4 kilometers down the ocean floor, so that's the volume of water that's exerting pressure on your head. So hence the pressure is maximum at the ocean floor. And temperature and pressure have a major impact on the speed of sound. There is salinity, but it doesn't affect the speed of sound drastically as does temperature and pressure. So here's a graph of ocean temperature versus depth. This is a different graph. It's designed to pictorially represent the ocean as such. So first, on the x-axis, you have the ocean temperature in degrees Celsius, and on the y-axis, you have the ocean depth. But in every single graph, we're used to seeing 0 at the bottom, but in this graph, the 0 is at the top, whereas the depth keeps increasing. So we're going negative, we're going below, so the scale is negative. And it's actually depicting the ocean as such because here is the ocean surface and here is the ocean bed. And the color is also visually representing the ocean because sunlight doesn't penetrate to the great depths. So sunlight penetrates to a certain extent, and then there's this twilight zone, and then there's this black zone or midnight zone. So there is literally no light there. So now let's look at the curve. So the curve depicts how the ocean temperature changes with respect to the ocean depth. So initially at the ocean surface, it's warm because sunlight heats up during the day. and the temperature decreases gradually as you go deeper and deeper, but it's a very slow decrease because sunlight still penetrates to a great depth, to a certain depth during the day. But then after that point, there is a sudden drop. So because in this region, the sunlight no longer penetrates, and then the temperature keeps decreasing and approaches very close to zero at the ocean floor. So this is the profile of ocean temperature with respect to the depth. So let's talk about ocean pressure with respect to depth. Now, the hydrostatic pressure is given by this equation, P equals rho g h. So it depends on the density of water, the acceleration to gravity, and the height of the water column. Now, we're going to make some assumptions here. First is about density of water. We're going to say density of water is constant at 1,000 kilogram per meter cube. Now, actually, in reality, density of water is not constant because when you're going deeper and deeper, the water gets colder and colder, and the cold water is actually heavier than the water at normal temperature, and that's the reason why the cold water sinks. So the cold water is slightly denser than normal water, but we're going to assume that it's the same just to make the calculations easier. And another thing is about the acceleration to gravity. Now, when you're going deeper and deeper, you're going, getting closer to the center of the earth. So there is less mass that is exerting a pull on you, but on the other hand, there is the mass above you, which is exerting the opposite pull. So the net gravitational force on you if you're going down is actually decreased compared to if you're on the surface. But let's look at it practically. Even if you're going at great depths, for example, 7 kilometers deep into the ocean floor, still the radius of the earth is like 6,400 kilometers on average, and 7 kilometers is very negligible compared to 6,400 kilometers. So even if you do the calculation to find out the acceleration to gravity, the acceleration to gravity is marginally decreased. So for most practical purposes, we can assume that it's 9.8. So if density is constant and acceleration to gravity is constant, so there's just a linear relationship of the pressure with respect to the height. So thus the hydrostatic pressure increases linearly with the ocean depth, and we can see it pictorially in this graph. So in this graph, we have the x-axis. Here is the water pressure in bars, and on the y-axis, we have the ocean depth. Again, the value starts from 0 and goes all the way down to minus 7,000, which represents the ocean floor. And we can see that the curve is just a simple linear line because there is a linear relationship. So at great depths, where the ocean pressure is very high because of the height of the water column above it. Here's a graph of speed of sound versus depth. I got this graph information values from Wikipedia. So this is strictly for ocean water, which is a salty water, and salt water has a different density compared to fresh water, so the speed of sound is going to be slightly different. So as we can see here, again, the graph represents the y-axis is ocean depth and the x-axis is speed of sound. So at the surface, the speed of sound is greater, but then it gradually decreases to a certain point because the temperature of water is decreasing, and the pressure has not a great effect on the speed of sound at this region. So and at one point, it becomes the minimum. So this is like the sound speed minimum, and then after this range, although the temperature keeps decreasing further and further, but it's not as drastic as the pressure increase. The pressure increases linearly, and the decrease of temperature has no effect on the speed of sound, but rather the increase in pressure has a greater effect on the speed of sound, and it keeps increasing. So this is the graph. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.